Okay, now to quickly wrap this up, we're going to look at resistors in parallel now. The definition, of course, being that there are multiple conducting paths. So when we draw this circuit, there's lots of different ways that we could do this, but the current can go through either this branch or this branch or this branch. Those are supposed to be little resistors in there. And of course there could be multiples, but you have multiple different loops that the current could follow. So I'm just going to call this resistor 1, resistor 2, resistor 3. Of course it could be 2, 3, 4, 5, whatever. But in general, that's what the diagram looks like. Now, in this case, the current is not the same in all of them, because when the current comes out of the battery and gets here, some of it's going to go this way, some of it's going to go this way, and some of it's going to go this way. So the current's going to split up. And if the resistors aren't equal, it's not going to split up equally. More is going to go where it's easier, and less is going to go where the resistance is higher. So the current is not the same. But by the loop rule, if this takes me up, let's say 12 volts, so if that lifts me up 12 volts, by the time the electrons get through the circuit, they have to come back down 12 volts. And if they're only going through one resistor, then each of these resistors must bring them down the same amount, regardless of how big the resistance is. So in a parallel circuit, the thing that is the same that you should have seen last week is the potential difference. So in series, it's the current, but in parallel, it's the potential. And that's a good way to remember it, PP. Parallel is potential difference. So what do we know about the current? Well, I know that, again, the current coming out of the battery is going to split up. And some's going to go this way, and some's going to go this way, and some is going to go this way. So the blue and the purple and the orange together have to add up to that green amount that I started with, because the green splits. Some goes here, some goes here, some goes here. But once it comes back together again, it's all got to loop around and come back through the battery. So what that means is that the current in the battery is equal to the current in each branch added together. All right, so now moving on to potential difference. We just said the potential differences are equal. So whatever the potential difference of the battery is, that's the potential difference in the first resistor, that's the potential difference for the second, and so on. Okay, so in this case, how do you calculate equivalent resistance? Well, it's not so simple. There is a formula for this that you need to use, and that's because more resistance, more resistors, actually reduces the overall resistance. Because if I have more branches, that's more pathways. So more pathways actually leads to less overall resistance. Kind of like when we open up different highways or different routes to get somewhere, we're going to have less resistance. Like in our school parking lot, there's only one way out, so there's a lot of resistance. If we had two ways out, right, the resistance would go down. So this is the formula, 1 over Req is equal to 1 over R1 plus 1 over R2 plus 1 over R3, and so on. It is just like the 1 over P plus 1 over Q equals 1 over F equation we had a long time ago. I'll review with you how to do this, but it's the same math every single time for a parallel circuit. All right, so the steps here are going to be the same. First step is always find Req. Second step is going to be find the current in the battery. And the way we do that is delta V equals IR. The delta V is going to be the battery delta V. The R is going to be the equivalent resistance. And we'll divide those to get the current in the battery. And then we'll continue from there. And I'll show you more tomorrow how we're going to do that. Right, now, the main advantage for this is that if one goes out, the rest still work. Because it's just one of the branches is down, right? One of the highways is down. The rest of them still work. So that's definitely an advantage with Christmas lights. If one goes out, the rest of them can keep working. Another thing that's an advantage is that they all have the same delta V. And we actually use that in our homes. All of the outlets in our homes are wired in parallel so that they all have the same potential difference. That way when I plug into it, I know exactly what I'm getting. For our outlets in America, it's about 120 volts. So I know that number every single time I plug in. Now that's not the number in other countries. That's why you have to have adapters, because theirs is like 240, depending on where you travel, and other places have others. But the outlets, I'm sorry, I spelled that wrong. That looks weird. The outlets, again, in America are about 120 volts, and they all are because they are wired in parallel. Okay, so quickly, I'm just going to show you how to calculate equivalent resistance. When it's a series circuit, all you have to do is add the numbers together. So 3 plus 10 plus 5, that would be 18 kiloohms. So that would mean 18,000 ohms. So if I wanted to get the current in the battery, I would take the delta V of the battery and divide it by the equivalent resistance. I'm not going to take the time to do the math, but if I did 9 divided by 18,000, that would tell me how much current is flowing throughout this circuit. Okay, now here I have a parallel circuit, so it's a little bit different. The equation is 1 over Req equals 1 over 100 plus 1 over 200. So please grab your calculator and do this with me very quickly. You're going to do 1 over 100 plus 1 over 200. So that's step number 1. That's 0.015. But that's not the answer because that's 1 over Req. So you still need to take the reciprocal. So I'm going to just do 1 over that. So every single time, this is the steps to do parallel. And notice the answer is about 67 ohms. It is less than either of those resistors because you're giving options. Every time you add another option, the overall resistance goes down. This number will always be smaller than any of the resistors in the circuit. Okay, one more example. This would be 1 over, and I'm just going to pretend it doesn't say kilo to make it faster. 1 over 10 plus 1 over 2 plus 1 over 1. So on my calculator, I do 1 over 10 plus 1 over 2 plus 1 over 1. And then I do 1 divided by that number every single time. So the equivalent resistance would be 0.625. And that would be ohms. Okay, so here is your assignments. You have a worksheet that should be completed in class. You have a positive physics that should be done by tomorrow. And then there's a concept builder that's opened up. All of this is in Google Classroom. That's not going to be due until Thursday.